Yes.
Hello and good afternoon. The Public Outreach and Education Committee of the Astronomical Society of India welcomes you to the discussion series, Ask an Astronomer. I am Sarita Vig, and joining me are Professor Aniket Sule and Professor Harvinder Kaur from the ASI POEC. Also helping out with the organization are Atharva Pathak and Dr. Crispin Karthik. Our eminent astronomer for today is Professor Divya Oberoi from the National Center of Radio Astrophysics, or NCRA, Pune. And our theme for discussion is the Sun. Professor Oberoi will be giving a short presentation about the Sun, which will be followed by a discussion. I invite our participants and viewers to jot down their questions in the chat box. I would first like to introduce our guest astronomer and speaker. Professor Oberoi completed his BSc and Masters from University of Delhi in 1991 and 1993 respectively. He then joined the Joint Astronomy program for his PhD. As part of this program, he spent a year at the Indian Institute of Science to complete the graduate school and then joined NCRA for his doctoral research, which he completed in 2000. On the thesis topic, tomography of the solar wind using interplanetary scintillations. He held postdoctoral fellowships at LPC2E in Orleans, France, and MIT Haystack Observatory in USA. In 2005, he joined the MIT Haystack Observatory as a research scientist, and in February 2012, he took up the position of a reader at the National Center for Radio Astrophysics. He has a number of publications to his credit, and he is currently an associate professor at NCRA-TIFR. His research interests include solar physics, heliospheric physics, interplanetary scintillations, and interferometric techniques. He is also serving as the secretary of the Astronomical Society of India. May I now request Professor Oberoi to begin his presentation.
Thank you so much. Thanks a lot, Sarita, for a comprehensive and generous introduction. Let me share my screen and then we can get started. Okay. So I hope you can see the presentation on your screens now. Yeah. Okay, so let's get started. So thanks everyone for joining us today evening for talking to us about the Sun, and thanks to the POEC, the Public Education and Outreach Committee of the ASI, for giving me this opportunity. Okay, and my plan is to roughly talk to you for about half an hour, and then we will have the time for talking about any questions you might have and any discussion which comes up. Okay, so let's start by taking a look at some vital statistics of the Sun as it appears to our naked eyes. So in terms of its size and mass, the Sun is about 100 times larger in radius than the Earth, so at about 7 times 10 to the power 8 meters. In terms of mass, it also turns out to be about 1,000,000 times heavier than the Earth. Right, so you can imagine that roughly the density of the Sun and the Earth must be very similar. You all probably already know that it takes light something like 8 minutes to travel from the Sun to us. So in kilometers, that's something like 150 million kilometers. And if you measure it in units of radius of the Sun, it is about 214 times the solar radius. Okay. We know that the Sun is a very hot body. The temperature of the surface is something like 5,800 Kelvin. If Kelvin is an unfamiliar unit, it is a unit to temperature, to measure temperature. It is the same thing as centigrade, except the scale is slid by 273. So you add 273 to Kelvin and it becomes the temperature in degrees centigrade. The Sun gives out a lot of power. Its luminosity, which is the total amount of energy which it is giving out, is this number 4 times 10 to the power 26 watts. If you compare it to the power consumption on Earth, it is something like 10 billion times the power which mankind generates on Earth here. So the energy which is incident on the top of the Earth's atmosphere from the sun is what is referred to as solar constant, and it is about 1.4 kilowatts. And if we can harness a significant fraction of this energy, right there is the solution to our power generation issues. In terms of age, the sun is a sort of middle-aged star, about 5 billion years or so old. Okay. Now, in terms of its structure, we know that at the very center of the sun, right, something which we call the core of the sun, is the place where the nuclear reactions take place, where the hydrogen atoms combine to form a helium atom, and the tiny difference in mass between two hydrogen atoms and one helium atom is what is given out in terms of energy as gamma rays. And as these very energetic photons or rays of light, they propagate out from the core, they pass through what is called the radiation zone of the sun. And here this photon scatters many times from the other matter which is there. And it takes it almost hundreds of years actually to random walk its way all the way through this radiation zone. And then it comes to a place which is called the convective zone. It's called the convective or convection zone because at that place, the physical conditions are such that these photons, which are by now ultraviolet photons, are actually absorbed by the material which is there. And as the material which absorbs it becomes hotter, it tends to rise, just like it happens in your boiling tea kettle, that the hotter fluid at the bottom, the hotter water at the bottom tries to rise to the surface. So the hotter material at the bottom tries to rise to the surface, and the cooler material from the top tries to sink down, and this sets up these so-called convective zones or convective cells. And there are various layers of these convective cells which are present here. And what it appears like on the top, and this is something we will see in a small movie a little bit later as well, are these small granules like things, which are all really tiny convection cells which are taking place there. The other prominent feature which you see on the sun is something which we call sunspots. So now the sunspots have been known, of course, for a very long time. These were among the first things which were discovered about the sun. And I'm showing you a sketch here by Galileo Galilei, right, which dates from 1613, though the observations of sunspots themselves actually took place even earlier than that. And on the right, this particular image shows the variety of sunspots which were documented by this particular individual shiner around the same time as Galileo. And if you want to take a historical look at how people looked at sunspots, when they were discovered and what people thought about them, a very interesting place to get that information is something called the Galileo Project. So you can just look it up on the web. Okay. So now we understand these sunspots to be places on the surface of the sun where the magnetic field erupts out. Okay, so below the surface of the sun in the convective layer, there is an enormous amount of magnetic field which is present. And the places where it erupts from the surface of the photosphere, the visible surface of the sun is what we call the photosphere. Okay, photo standing for light in Greek. And so the places where the magnetic field erupts is what we now regard as sunspot. The reason why it appears dark is because this is cooler than the surrounding regions. Now, why is it cooler? It's cooler because, like I said, it is the convection which is bringing up the heated material from the bottom to the top. And when these magnetic fields are large, it inhibits this convection from taking place, and therefore the hotter plasma finds it harder to come up there, and the temperatures in these sunspots can be order 4,500, a little bit lower or higher depending on the strength of the magnetic field as compared to the almost 6,000 Kelvin in the neighborhood. Okay. Now the magnetic field, you know, is like a closed rubber band, right? It does not have an end. So if I pull out a magnetic field from the surface, there must be a place from where it is going to come out, and then there must be a place where it is going to go in, right? So it must always occur in pairs. So in reality, though, it should always be the case that as much magnetic field as comes out must go back in as well. What we find is that when we look at really detailed pictures of these sunspots, they don't always seem symmetric. There are many which are symmetric, and there are many others which are not symmetric. Here is a good example of something which is not symmetric. So here is a larger region from where some magnetic field is erupting, and we know that it must all be going back into these regions, but the size of those regions are smaller, so the magnetic field must be denser in these regions. And also, if you look closely, you will find many sort of uh, very detailed features, small strands like things. And if you want, you can imagine these to be really threads of your magnetic field, or striations in your magnetic field which are there, right? And now we are actually able to see some of these structures when we make images of the sun in light which is given out by very hot elements. So this light is taken at a wavelength, for example, which is sensitive to plasma at a temperature of about 600,000 Kelvin. Okay, and now you can see that all these structures which you see, these are actually magnetic field lines which are originating from the sun. You can see the loop-like structure, and you can see a lot of fine detail in these structures which are present here. Okay. Now, when people started to observe the sun, they very quickly realized that these sunspots, uh, their presence on the surface of the sun is not a constant. It sort of comes and goes. Sometimes they are more, sometimes they are less, but this variation is very systematic, right? So they realized that there is a sunspot cycle, which got named the solar cycle. And what this plot shows is, on the x-axis is time. It goes back quite a long time ago. And on the y-axis is a measure of how many sunspots were there on the surface of the sun at any given time. And so you can see peaks and valleys. And as is obvious, not all peaks are equally tall. Also, not all valleys are equally deep, right? Some valleys don't go to zero, but some others go to zero, like the most recent one as well. And also, if you look at the time interval between successive peaks or valleys, you find that it varies from somewhere between 9 years to 14 years, and the average is around 11 years. So we say that the solar cycle has a period of about 11 years. Now, this is just another plot of the same thing, except what I was showing you earlier was something called monthly smoothed sunspot data, in the sense that you make your measurements and sort of do an averaging over a month scale. And here the averaging period is much smaller, and you find that uh, there can be quite a fluctuation in the number of sunspots which you see even during the solar cycle. Okay. Very good. Now, people also realized quite early, actually, that not only is there a cyclic variation in the total number of sunspots, there is also a very systematic trend in where these sunspots appear. So the plot on the top is, excuse me, what is referred to as the butterfly diagram. Right? It has time on the x-axis, and on the y-axis is the latitude of the place where the sunspots appeared. And I've just drawn this line as a reference line at some particular solar minimum. And this is just to draw your attention to the fact that at the start of a new solar cycle, right, when the sunspot number begins to rise from a very small number, these sunspots appear at latitudes of around plus minus 30 or 25 or so. And as the cycle progresses, the latitudes at which these sunspots appear, they slowly become smaller and smaller and move closer and closer to the equator. And that at some point, there comes a time when there are very few sunspots on the earth, or on the sun, sorry. And then the new ones appear, and the new ones which appear, they again start from around plus minus 30 or so latitudes. And you find that actually sunspots don't go beyond some plus minus 35 or 40 degrees in latitude. So there are no sunspots really close to the poles. Okay. Now, these sunspots have really, so sunspots, like we said, are the places where the magnetic field erupts out from beneath the photosphere. And it is this magnetic field really which makes our sun so very interesting. And that is what I'm going to try to share in the next few slides. So on the left, or the only picture which you have right now, in fact, is a picture taken in X-ray light. Okay. And there is one picture taken every year. So one representative picture for every year. And this entire collage shows you an entire solar cycle. Okay, at the very back where my cursor is right now is the solar minimum, where the sun was featureless in terms of sunspots and the sun appears very dark in X-rays, while at the front here is the solar maximum, where the sun, you see, has many patches of bright emissions. Right, this X-ray light is emitted by really hot plasma, and we now know that this hot plasma is associated with where these active regions or sunspots are. If you were to take a look at the sun at much cooler temperatures, these temperatures are actually a little bit less than 5,000 Kelvin, maybe 4,800 or so. And here again, you see the featureless solar minimum at the back. And here again, you see the much brighter regions, which are all again associated with the regions of strong magnetic field erupting from the photosphere in the surface. Not only that, now we also know that from the sun outflows a very tenuous flow of plasma all the time, right? Which we now call the solar wind. So here is the same plot, but this time for solar wind. And if you look at the one corresponding to the solar minima, it shows that there is an equatorial belt where these reds and yellows colors appear. The red here corresponds to something like 400 kilometers a second. And these blues here correspond to something like 800 kilometers a second. And so it is telling you that the wind which is flowing out, this plasma which is flowing out from the sun, it's very well organized into a structure where there is an equatorial belt of slow solar wind, and most of the surface of the sun is covered with the fast solar wind. But closer to a maxima, the whole surface is sort of covered with comparatively slow solar wind. And occasionally there are patches of fast solar wind, sometimes at the poles, but sometimes at other places as well. Okay. Now let's try to understand why this comes about. So I'm showing you here two pictures taken during a solar eclipse. If you look at the one which is to our right, this one was taken close to a solar minimum. Now, you can see an enormous amount of structure in this medium around the sun. The structure I'm alluding to, or I'm referring to, is the structure not on the surface of the sun, but in the region surrounding the sun. Okay, a little bit of cheating was done here to superpose an image taken just a little bit after the eclipse from a satellite to make this look very pretty. Now, what this reminds you right away of is something like a bar magnet, that if I have to place a bar magnet here, there is maybe the North Pole, here is maybe the South Pole, and that is what the magnetic field would look like. Now, we know that actually we can't see magnetic field, right? So how are we able to see this structure? What is happening here is that this magnetic field has actually trapped the plasma, and it is the electrons in this plasma which are reflecting the light which is being given out by the sun, and that light is what is reaching our telescopes, and that is allowing us to see these magnetic structures. So what you're seeing here is that close to a minima, the magnetic field of the sun is sort of quite ordered. You can have a distinct north and south pole, and you have some other features as well, but this polarity and this strong north and south nature is very evident. But if you look at the panel on the left, if you look at the sun, you close to a solar maximum, there is no way you can, by just looking at this picture, figure out where might be the magnetic north and the magnetic south pole on the sun, right? The field is much less ordered in that sense. And there are sunspots over a large part of the sun, and the magnetic field does not have a large scale ordering. And that is really what was giving rise to the various patterns which we were seeing in the back for the solar wind, as well as for what I was showing you in X-rays, as well as in the extreme UV. Okay. Now, let's take a look at what the sun appears like as we step through temperatures. Okay, so what this movie is showing is various images of the sun taken at exactly the same time, but at temperatures or in light corresponding to temperatures which go all the way from around 5,800 Kelvin to about 3 million Kelvin. Let me run through that again. Pay attention to where these sunspots were and how do they change as we go to hotter and hotter plasma. Okay, so the places which were actually the places which were dark in optical light, because we said they were cooler because convection couldn't take place there, it turns out that they also are home to much hotter plasma. So that seems a little bit like a contradiction. So let's try to take a look at it using this picture, which shows you the sun at the same time, but taken in many different temperatures from an observatory called the Solar Dynamics Observatory. So if you look at, let's say, one of these panels, this is what the photosphere would appear to us if we were to look at it with our eyes. I'm not advising you to look at the sun with your eyes, please. So it's very dangerous to look directly at the sun. Never do that. So this is a wavelength corresponding to 4,500 angstroms. Here is the temperature it is sensitive to, and it is telling you this information, or this light is arising from the photosphere. And we will look at, let's say, the bottom two rows in this panel. And as you go from left to right and top to bottom, you'll find that these temperatures keep increasing. And by the end, it goes to something like 10 million Kelvin. Now, I want to point out a few things. Let's say if we compare this image at 6,000 Kelvin with this image, middle panel, extreme right, at about 1,000,000 Kelvin, right? There are a few things which you can see right away. So for example, at 6,000 Kelvin, the sun had a very well-defined edge, a limb, as the astronomers call it. But by the time you're here, you find that there is actually some diffuse light coming up from above the edge of the sun as well. So, and like I said, this light is given out only by very hot plasma. So there must be this hot plasma which is sitting here. You also notice that the regions which were dark here turn out to be exactly the regions which are bright in here, right? So somehow this magnetic field which is erupting out of here is responsible for doing something which is giving rise to plasma at such high temperatures. And the same trend actually you can see continues all the way to 10 million Kelvin, except when you get to say something like 6 or 10 or maybe even 2.5 million Kelvin, you find that all that hazy structures which you could see very well at about 1 or 2 million Kelvin are no longer there. The limb of the sun is again more well defined. Okay, so this actually brings us to something which we now call the coronal heating problem, and the basis of that is the following. So at the base of this figure is the base of the sun, the photosphere, and what this solid curve is showing you is the temperature of the corona, as shown here. So as you go higher up, you enter something called the chromosphere, which is where the absorption lines from the sun appear, and the temperature drops slightly. But then you encounter something called a transition region, which is very thin, less than 1,000 kilometers or so, where the temperature of the corona rises by something like almost a factor of 100, 2 orders of magnitude. And corona, by the way, is just the Greek word for crown, right? So whether it is the coronavirus or it is the solar corona, it still refers to the crown. And so what we find is that in this corona is sitting at a temperature of something like 1,000,000 Kelvin, even though it is sitting on top of a photosphere, which is at a temperature of just something like 5,800 Kelvin. This is what is referred to as the coronal heating problem, right? The corona is much, much hotter than the photosphere. And we all know that the heat must always flow from a hotter body to a cooler body. We also know that the heat in this case must be generated inside the sun, right? It is not the corona which is generating heat, which is heating up the photosphere. So, so we certainly know that none of these traditional mechanisms for flow of heat, conduction, convection, or radiation can give rise to this, right? So there must be some other way of making this corona so hot, okay? And what happened? Yeah, okay. So what I'm showing you here is a movie, a great zoomed in version of a section of the sun, which is the quiet sun. And what you are seeing here on top are the small convection cells, which I was talking about. And if you look at them, you see there are sort of small irregular motions which are taking place. You can almost imagine new material coming up, old material going down, the regions where it is all dark. So what one needs to do is that uh, you need to find some mechanism using which you can transport the energy from whatever is sitting here into your corona. And we know that the whole of the sun is actually populated by these magnetic fields. And what we understand now, it is the energy in these magnetic fields which is being used somehow to heat up the corona. And what I want you to imagine is that there is magnetic field coming out from each of these dark spots. And as these dark regions move, it is going to set that magnetic field in some sort of a motion. right? So you can imagine setting up some waves in these magnetic fields, and if you can get these waves to lose their energy in the corona, then you have found a way of heating the corona. And this is one of the proposed mechanisms for heating the corona. It's called the wave heating hypothesis. There is yet another mechanism which is called magnetic reconnection, and for that, what I want you to do is I want you to think of a magnetic field as a rubber band or some sort of an elastic string, right? Now, as these motions are taking place, it is going to turn the magnetic field into a spaghetti-like structure, into your noodles, Maggie noodle sort of a structure, which is very tangled. And as just like in a rubber band, if you keep on say turning and twisting an elastic rubber band, you keep adding stress to that, and at some point it is going to break. Right? A magnetic field cannot break, but what it can do is something called reconnection. That if you look at the vertical two arrows, there is plasma being pushed together. These red and blue lines, they indicate the magnetic fields. And if the plasma is pushed together such that opposite magnetic fields are coming close to each other, it can sometimes happen, if the conditions are just right, that these oppositely directed magnetic field reconnects, and the topology of the magnetic field or the shapes of the magnetic field can completely change. So we believe that this process is actually going on all the time in the corona to relieve the stresses in the magnetic field which are being built up by the constant churning motions at the base of the convection zone. And it is the release of this stress which is actually heating up the corona. Okay, so that is here is, and this release actually not only just heats up the corona, it also gives rise to massive events on the massive flares and explosions on the sun. Here is a cartoon which maybe I'll skip over, but I'll show you this. So these things are called coronal mass ejections, and you can see them as sort of wisps of light going away. Let me first tell you, however, what are you looking at, right? So here is a picture of the sun taken in some particular wavelength. What has been done is that an artificial eclipse of the sun has been created. These are taken from a spacecraft sitting along the sun-Earth line. And what they are looking at is the light in this corona, which is reflected off, or yeah, what they are looking at are the electrons in this region, which are reflecting the light which is coming from the sun. So the brighter something is, more density there is. Okay, and what this movie is showing you essentially, that usually nothing much is happening, but occasionally, just like now, there was something which flew out from the sun, right? And let me just play this movie once again. And these things are enormous amounts of material carrying enormous amounts of magnetic field, which are just moving out. Okay, and sometimes when they are directed towards the Earth, it so happens that like what you're seeing now, all this snow which used to be there in say television sets in 70s and 80s, what you're seeing, these white things are actually these energetic particles hitting the sensors which are making these images. Okay, if they happen to be directed towards the Earth, they can have a significant impact on our technology these days. Here is another animation which shows the same thing. So this is the sun from where this very hot plasma has just taken off. It is now moving towards the Earth. And as it gets close to the Earth, it hits the magnetic blanket of the Earth, the magnetosphere. And in this particular case, most of the plasma has gone through along the sides of the Earth's magnetosphere, but some of it via magnetic reconnection has come back close to the terrestrial north and south poles, where it is giving rise to the aurora. Okay, so what I'm trying to say here basically is the following, that if this was a coronal mass ejection, let's say its magnetic field was oriented this way, and here is the Earth with its magnetic shield, and let's say the magnetic field of this magnetosphere was oriented this way. As the CME comes and hits here, you have two parallel magnetic fields coming close to each other, and as we know, parallel magnetic fields repel. So the consequence is that this just pushes against this magnetosphere, but most of the plasma flows along what is shown by these yellow lines. However, if opposite was the case, if this magnetic field was oriented the other way, and when it comes here, there are two oppositely directed magnetic fields which can come close. What happens is that there arise opportunities for magnetic reconnection, and lot of this plasma can then flow along these yellow lines, and it is going to flow along the magnetic fields. So it is going to end up close to the magnetic north and south poles of the Earth. That can have really quite dramatic impacts on our technology reliant society, which is I'm trying to summarize in this picture here. So for example, we now have astronauts living all the time in the International Space Station. Suddenly they are being bombarded by this very energetic plasma, right? You have, for example, airline flights which are often going close to the poles. So for example, a typical flight from India to US will go close to the North Pole. If you have these energetic particles there, you don't want to carry passengers there. So the airlines are forced to take longer routes to get there. All these electrons which come along the magnetic field, they are setting up now currents in the ionosphere. Now, those currents are going to induce a magnetic field, which is in turn going to induce another current on the various conductors which are there on the Earth. The longest ones are our electricity grids. So it can actually disrupt that power supply. It can do a whole lot of other things. You can lose your GPS tracking mechanisms and so on and so forth. So it is actually becoming quite important for us to be able to understand and predict these things. Okay. I'll Okay, how am I doing on time? Not too well. Let me just show you some small glimpse of what it might be like to look at the sun with radio eyes. Okay, the sun in optical eyes actually does not vary very much, but if you were to look at the sun in radio wavelengths, it can be very, very variable. And here I'm just showing you two examples. This yellow disk here and this black disk, black circle here, they are supposed to represent the size of the sun. And these colors are supposed to represent how bright is this. If you just look at these numbers, this is 10 multiplied by another 10 to the power 8. That is the brightest thing here. So some 10 to the power 9 in some units. But the quiet sun is something like just 10 to the power 5. Okay, so things can happen on the sun which can outshine the rest of the sun by factors of 10,000 in radio waves. There's a Diwali card which I wanted to share with you. Let me see if I can. Sorry. So this was just something which a student of mine made. Why can't I get rid of this? Okay. Sorry, too fast here. So this was made out of real data, and each of those explosions was lasting about half a second. Okay, so there are a lot of these small things which are happening all over the sun, and these we think are actually the first signatures of those reconnections which I was talking about, which are responsible for heating the solar corona. Maybe I'll skip and try to go towards taking questions. So the thought which I really want to leave you with is that the sun, even though it is our closest star, something we can observe in great detail, it continues to host many, many unsolved mysteries. Okay, and a lot of effort is currently being put in all kinds of new missions from the Parker Solar Probe and Solar Orbiter in our satellites, flagship satellites from NASA and ESA, which have both recently been launched. On the Earth, there are many new telescopes which are being built to study the sun, including the Square Kilometre Array. And as you all know, our ability to do computation is much better, right? Your cell phone now has a better processor than the computer on which I wrote my thesis. So many problems which were simply not possible earlier are coming now within reach. So it's really exciting time now for solar physics, and we are hoping that really over the next 5 or so years, we would have managed to solve some of these really perplexing mysteries about the sun. Okay, and with that, maybe I'll stop here and get into a discussion or take any questions. Yeah.
Yeah, thanks, Divya.
Yeah.
Uh, well, before we take any questions from the audience, we would like to know more about the work which you do with Sun. You have
Okay.
spoken about in the last one or two slides about radio sun, but we would like to
Right. Yeah.
understand how radio sun, the observing sun in radio wavelengths is different from observing it at very short wavelengths.
Okay.
And
Well,
exactly what do you observe? Which physical process do you observe?
okay. Thanks. Let me go to something like this. Okay. So the part of the electromagnetic spectrum which I observe the sun is what is called the radio part of the spectrum, and this is the okay this the emission from the sun, like from any other star, is like a black body, right? It has a peak somewhere, and as you go further and further away from that, the emission falls. Okay, the part of the sun which I study is really what is shown here. Uh, what is really exciting about this part of the sun is actually you're not studying what you would be able to do in optical or in at other higher frequencies, which is basically the photosphere and the high magnetic field regions there. What we are studying is actually the corona, okay? Because that is the place where the emission from the sun is uh, is prominent at these frequencies. The corona, like I said, is at the temperature of about 1,000,000 Kelvin. Okay, so the emission which we study at radio frequencies, which I personally study at radio frequencies, comes from the corona. It is practically invisible in the optical and higher frequency band. So you will never get to know much about the corona at those frequencies. And my prime interest in the past many years has been trying to see if we can understand coronal heating by finding evidence for these numerous small explosions which must be taking place because of really tiny magnetic reconnections, which are individually too small to see, but collectively they have enough energy to be able to heat up the corona. So that has been one of the areas of my emphasis lately. And that Diwali card, which a student of mine had made, Rohit Sharma, I should have given his name, is one of our attempts to look for these really tiny events which are taking place here.
So are these tiny events observable through amateur radio telescopes, or you need a really big size telescope for this?
No, they are not observable using amateur radio telescopes because so you need to make an image of the sun. Okay, imagine the following, right? Following the example from that movie. It is Diwali night and you are hearing a lot of crackers. So you're hearing a constant rumble, but you're not able to make out an individual bomb or whatever, right? So what we are trying to do that in this rumble, we are trying to look for individual events which are taking place. Now, each of these things lasts for a very short time, take place on a very small patch on the sun, and the signal it produces in radiation, in the radio spectrum, is also over a very small patch of the spectrum. So you have to isolate this in space on the surface of the sun, in time because it lives for a very short time, and also in frequency because the signature is confined to a very small part of the band. That requires you to make an interferometer which can image the sun very quickly, right, in half a second and over a very small part of the electromagnetic spectrum. So right now, it takes actually the state of the art equipment or telescopes to be able to do it. Amateur astronomers will not be able to do that. Yeah.
Okay, so let me take some questions from the audience. Uh, First two questions by Ayush Tiwari and Varun Nikam, they can be combined in some sense. So Ayush wanted to know how the age of the sun was calculated, and Varun wanted to know how you know about temperature models of sun's core or at the surface. So essentially, both pertain to solar model. So what
Right.
can you
Yeah.
tell?
Okay, so by now actually we have built a fairly detailed understanding of stellar evolution. So the age of the sun really comes by understanding a very large number of stars in our galaxy, for which we can get pretty detailed models, and a lot of theoretical calculations are available for uh, how a given star from its formation to the stages of its death evolves. And it typically involves the study of a large ensemble of stars and uses what goes by the name of the Hertzsprung-Russell diagram, which has essentially the the temperature of the star, how hot is the radiation which is coming out from the star, and the luminosity, the total amount of radiation which is coming out of the star as its two axes. And you can see a star follow a particular track on this plot. Maybe actually if I was to do a quick Google, I can pull out the HR diagram. Yep. So by finding out where your particular star lies in that figure, you can find out where is it in its stage of evolution. Okay, so you need a little more background to be able to do that. But if you're really curious about finding more about this, look up Hertzsprung-Russell diagram on the web, and you will find much more detailed information. And about finding out the detailed structure of the sun. So just like we do seismology on the Earth to figure out what is the structure of the Earth, right? We know that, say, when an earthquake takes place, very quickly we have a report that it was so much on the Richter scale, and the epicenter was at this place, and it was so many kilometers beneath the surface of the sun. And all of that we have figured out by looking at how the waves propagate inside the Earth's Earth's crust, and actually even deeper. So a similar study is also done for the sun, and that field is called helioseismology. And that is looking at small oscillations which are taking place all the time on the surface of the sun. And using that, we are able to figure out how does the sound propagate inside the sun. And this propagation of sound depends on great details of what is its mass, its temperature, its pressure, and composition. And using that, we are able to figure out what are the details of various regions, how deep is the convection layer, how much deeper is the core, and so on and so forth.
So, so for example, if I rephrase what you just said, so there are some acoustic oscillations happening on the surface of sun, and we can see those frequencies. Since we know many different modes of the frequencies, many frequencies which are present on the surface of sun, we can use those to model all the free parameters which we have. So each of the variable which you they asked about the temperature or pressure or density, each
Composition,
of
yeah.
them is a free parameter, and using
Correct, yeah.
those many different frequencies, we can constrain those parameters.
Parameters, exactly, yeah.
So, okay, the next question is by Apurva. How does magnetic field exactly, field lines exactly trap gas?
Okay. That's a very interesting question. And that's something which I should have said, but I forgot to say. So you should think of magnetic fields and plasma as essentially magnetic fields forming some sort of a string, and the plasma forming the beads which are on that string. Okay. When the gas is very highly ionized, when the gas is really very hot, this is the sort of relationship which they have. Okay. So if you move the magnetic field, that is, if you move the string, the bead is going to come along with that. Or if you move the bead, there is no way to move the bead without dragging the string along with it. Okay. So what happens here is that you can imagine two kinds of situations. You can say that I have a very firm string, let's say some sort of an iron wire, and I have a small plastic bead on top of that. Now in a case like this, it is your iron wire which is going to decide how the plastic bead is going to move, right? Because it is much stiffer and has more energy, or it's much stiffer. In case of a magnetic field, this is exactly the situation where the magnetic field energy is much greater than the kinetic energy of the plasma which it is trapping. The other extreme might be that I have, like, say, some metal balls, which are my beads, and I have some ordinary string, which is my which I'm using as my string. So in such a case, it is the metal ball which is going to decide where to take the field along with it, or where to take the string along with it. And that is the situation where the kinetic energy of the electrons is much, much higher than the magnetic field's energy.
Okay, thanks. Ballal Patil wanted to know how long can a sunspot typically last? And I will also add another question from Varun Nikam, which any explanation about periodic nature of the solar cycle?
Okay, so the ages of sunspots can range from anywhere from a few days to multiple solar rotations. Each solar rotation is almost a month, 27 days or so, and they can last for multiple solar rotations, so many months. So that can be quite a range. The second question was about what is the explanation for the
Why there is a periodicity
periodicity.
of solar cycle? Yeah.
Okay, so that again is a very interesting question. So what happens is that in any system, like, or in any star, left to itself, the magnetic field will actually decay. Okay, so in order to sustain the magnetic field, something has to be in operation, and that we call the dynamo cycle in the case of our sun, and that is actually the motions of the plasma in the convective zone of the sun. Okay, so something like the top 30% of the sun in terms of its radius is what is the convective zone of the sun. Okay, the plasma inside this is under constant motion, and because this is plasma, you can think of it as generating currents. Whenever you have currents, you are actually generating magnetic fields. And it is these motions which are generating the solar magnetic field. Now, it turns out that for a star like the sun, if you work out the natural time scale at which these cycles will operate, it turns out to be order 10 years, 11 years or so. Okay, so I'm sorry, I'm not giving you a more detailed answer than that, but it's a play of the various parameters involved, the size of the system and the amount of plasma which is involved in that. The time scale turns out to be order 11 years. There's an extremely interesting book by an Indian scientist, Professor Arnab Rai Chaudhary from Indian Institute of Science. It's called The Third Cycle of Nature. It's a beautiful account of not just historical account of how we learned about the sun and its magnetic field, but also a good pop science account of how this magnetic field comes into being and the solar cycle. So if you can get access to that, that's a very interesting book to learn from all these things here.
So Harsh Saria has a question. What does it mean to take images at different temperature?
Ah, very good. That's again a very interesting question. So, okay. So when I was talking about taking images at different temperatures, I was talking about at temperatures which were typically higher than the optical temperature of the sun. What I was actually referring to is that, you know, any atom, it has a bunch of protons and neutrons at its center in the nucleus, and it has some electrons which are going around it. Now, if I heat this thing up slowly, I can knock off more and more electrons off of this atom. Every time I knock off some electron, it has absorbed some amount of energy to do that. And every time the atom recaptures one of the electrons, it has given out. That electron has lost some energy to come there. So what we do is we make telescopes which will observe exactly some particular transition of some electron from some high energy state to a low energy state. And that transition requires a certain amount of energy, which corresponds to a given temperature. So that is how we are able to say that this light is coming from material which is at this particular temperature, because that particular ionization state of that material is able to exist.
Okay. Uh, Amrit Shankar Mishra has asked, will it be ever possible to study the cycles of spots on the surface of other stars?
Oh, indeed. It's actually possible already. We already know of a good few other stars which we know are quite magnetic. And in fact, the magnetic field on our sun is actually not very high as stars go. There are many stars where the magnetic field is much higher and is able to dominate the appearance of the sun even more substantially. So people believe even the light which they observe from the sun is modulated by the presence of the sun stars on sunspots, sorry, on those stars. Though you should, I guess, call them not sunspots, but star
Star
spots.
spots.
Yeah.
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 But so do we have enough data about other stars to see any cycles there, or we don't have enough data?
To the best of my knowledge, we don't yet have enough data to pin down cycles, but we have seen data where across the rotation of the star, we see modulation, which we believe is because of presence of star spots. And we have seen flares from stars, the so-called magnetic stars, which give rise to flares, which are very firm indicator of magnetic activity on these. So, but we don't have enough sustained observations to be able to pin down the cycles.
Okay, I will take the next question. Uh, Varun has asked, what causes coronal mass ejection and is it periodic like solar cycle? And another question which has come to us is the CME, your animation showed CME meeting the Earth in same direction. So it was repelled because of the magnetic blanket. What happens if it comes in a perpendicular direction?
Okay. Okay, so I'll go to the first one first, which was about are CMEs periodic, just like the solar cycle? Yes and no, because the CMEs arise from these sunspots. The sunspots are periodic, right? Or at least, I mean, maybe it's not good to say sunspots are periodic. The occurrence of sunspots follows a cycle, right? There is more of them every 11 years and so on. Yeah. So because CMEs take place from the magnetic field, which is coming out of the star, coming out of the surface of the sun, there are many more of them at the solar maxima than they are at minima. So at solar maxima, roughly something like 3 to 4 CMEs per day take place. And close to solar minima, maybe every other week there is a CME, or every 8 or 9 days, every 10 days or so there is a CME, something like that. Yeah. Why do they take place? That's again a very interesting question. Some things we understand is that uh, once the magnetic field is being churned up, it can sustain only so much stress. Once that stress exceeds some threshold, it has to relax somehow. Now, there are only certain situations in which such a large amount of stress is allowed to accumulate before it relaxes. Most of the time, it relaxes much earlier. Okay, and so you don't get a huge explosion, but you get many minor things which are much more frequent. But under special circumstances, more stress can build up than what is usual, and when that lets go, that is when a CME takes place here. Okay, and sorry, I've forgotten
The
what the
second
second
question was
question.
that if the if Earth's pole is perpendicular to direction of CME,
Huh.
then we are easily saved. But what happens if it is not?
Right. So you're saying that, let's say, if the magnetic field from the Earth was in this direction and the magnetic field from the CME which was coming is in this direction. Uh, so what you can do is, one way to think of it is you think of it in terms of components of the magnetic field, right? So there is the magnetic field in this direction. You say that, okay, I have, let me call this for the sake of ease, say some Z direction and some X and some Y. So I have this some field in the Z direction and my CME was coming like this. However small, it is also going to have some field in the Z direction, right? So it is the interaction between the fields of the Z directions of the two, which is going to figure out, which is going to give rise to how much energetic plasma is going to reconnect, or how much that magnetic field is going to reconnect with the Earth's magnetic field and then get directed to the Earth's magnetic poles. So that's maybe one way to think about that here.
Okay. So tomorrow is solar eclipse. We should remind
Ah,
our viewers. And
sure, yeah.
next question is actually a bit relevant to that. Uh, Ballal is asking, can the fluctuations of the magnetic field be predicted? So in the so typically during solar eclipses, we do see some images predicted by various
Right. Yeah.
groups.
Yes, yeah. So correct. So it is, so again, the answer to that would be sort of yes and no. Uh, at a very small scale and on a very short, okay, if you remember one of the movies which I showed, which had these sort of what we call super granules, which was the surface of the sun, which seemed to be sort of bubbling up and down. If you want, and all those dark lines in there were regions on the sun from where magnetic field was emerging. If you want to make a prediction of that, that we have no way of doing. Okay. But if you want to make a prediction of what is going to be the large scale features on the sun, having fed in your model the best information available about the sun from the past some time, that we are now slowly getting better and better at doing. So the large scale features which don't vary rapidly in time, okay, those we are able to, we are now much better at predicting those. Okay.
Okay. Kedar Soni has asked, would the magnetic poles be brighter in radio, say L band, as compared to the disk?
So uh, right now we don't find them to be brighter. Yeah. So you have to remember that it is not the magnetic field which is giving out the radiation. It is the plasma which is trapped there, which is giving out the radiation, right? So if I may have very strong magnetic field, but less plasma, and that would make it fainter. Now, what happens at the magnetic poles is that the field is open. By open, I mean that it is not a loop which is connecting back to the sun, or it is such a large loop that it is going quite, so if this was the, say, north pole of the sun, the magnetic field is going quite far from the sun. So it is not able to retain the plasma that much. The plasma is able to flow out along these lines. That is why, for example, you have the higher solar wind velocities away from the equatorial regions where the magnetic field is open. So because there is less plasma there, you don't find that much radiation. So you actually get more radiation from the equatorial region where the bulk of the magnetic field is closed here.
Okay. So next, I will again combine two questions. So one question is sun affected by other stars around us, and how how sun differentiates our solar system from rest of the galaxy?
Okay, so to the best of our knowledge, our sun is not affected by other stars in the solar system, other stars in our galaxy. So the next nearest star is Alpha Centauri, which is at about some 4.2 light years away from us, right? So it's an enormous distance for a star to exert its influence. So there is no way any other star is actually going to influence what the sun does. And the other question is also something very interesting, which is what is the sphere of influence of the sun or any other star in that sense, right? Yeah. So at the surface of the Earth, this solar wind which is flowing out, it amounts to something like 8 particles a cubic centimeter. Okay. As you go further out, it is only going to become less and less dense, right? Because the same material is being spread in a larger and larger volume. And at some place, it has to find equilibrium with what we call the interstellar matter. Okay. And now actually we have direct measurements of where this boundary lies because of satellites by the name Voyager. Voyager 1 and 2 were satellites launched something like 45 years ago now, or maybe actually close to 50 years. I forget the date of exact launch.
Yeah, I think 72 or 73, something like that.
Okay, so we are close to 50 years now, right? And they have actually crossed over into the interstellar medium now. So they have crossed over the region from where the plasma which they were measuring was of solar origin into a region where the plasma which they are now measuring is from the interstellar medium. So that boundary lies at the place where these two very, very rare medium, very, very tenuous mediums come into pressure equilibrium. And because the solar wind itself is variable, like you saw, there are these coronal mass ejections and so on. So this boundary also keeps shifting. Okay, so in fact, it so happened that one of the Voyagers, it crossed the boundary twice because the boundary itself shifted to come to make Voyager come back into the heliosphere and then pushed it out again. Yeah.
So there is one question by Akash that like Earth has a solid surface. If we go inside the sun, would we ever encounter a solid surface anywhere? And he also wants to know what exactly is plasma.
Okay. So about the solid surface, so certainly the photosphere is not solid. Beneath that is a layer of fluid, which we talk about in terms of a convection cell and so on and so forth. Beneath that lies what is called the radiative zone. Uh, I'm not sure if you would call that solid. It is certainly not fluid in the sense that there is no convective motion or something like that happening here. Uh, Maybe you would call that a solid surface. I don't know. Does anybody else want to jump in and make comments on that? Yeah.
Yeah, probably we cannot call that as a solid thing. It is in the sense the properties which are of that zone, they don't really correspond to properties of solid. So uh, for example, the distance between the particles will be
Hmm.
changing. The
Right.
particles
Yeah.
are in motion. So in that by that
Okay.
definition, it is not solid.
Yes, indeed. Yeah. And sorry, please remind me of the second part of the question.
What
Yeah.
exactly is plasma?
Ah, okay. Very good. So the material which we see around us is is comprising of matter where in any given atom, let's say there are some number of protons, and the electrons which are going around it are exactly equal to the number of protons. So even the smallest matter particle which you can take is electrically neutral. Okay? The world around us, that is how it turns out to be. But it turns out in the universe, most of the matter is not in this state, in the sense that the number of protons which are there in the nucleus, the number of electrons going around it is not exactly equal. It's usually slightly less. There is typically an electron or two, depending on the atom which you are talking about, the element you are talking about, and the temperatures which are involved, which are missing from the shells of these things. So such matter, such ionized matter, is what is referred to as plasma, especially when it is in the gaseous state here.
Let me ask just one more question, then I will also ask Sarita to jump in. But one question which I found interesting is somebody has asked, we say that there is 75% hydrogen on sun. If that is the case, why there is only less than 1% hydrogen on Earth? Why the chemical composition is so different on sun and Earth?
Okay. So there are probably many aspects to the answer, and I probably know only some of them. Yeah. So one reason for that is that because of the Earth's gravity, hydrogen is the easiest gas to lose. Okay, because so even if you had, I mean, certainly we would have had much more hydrogen in our atmosphere at an early time. And over time, we have been losing it just because the gravity of our planet is not strong enough to retain it. Okay, that would certainly be a part of the answer. I don't know if there are many other aspects to this question which I may not be well informed about here.
Sarita, I believe we have some questions from Facebook as well.
Yeah, but I
So
think there's one question that we can ask. This person has been asking, Akash Ramadugu, here in Zoom. He says, after the sun dies, what would be its next phase? A black hole, a neutron star, brown dwarf?
Okay, the sun is a sort of low mass star. By definition, it's exactly one solar mass. So, for stars of that mass range, they don't typically have very spectacular end of life stages. So it will turn out to I mean, I'm blanking out on what should be the appropriate state here. Yeah. It's not massive enough to give rise to a large supernova remnant or a big neutron star. Uh,
so mostly planetary nebula and white dwarf.
Yeah, white dwarf.
yeah.
Okay, so I think before I have some question which I think will be very useful, but before that, maybe we can ask Harvinder to ask some questions which have come up on YouTube.
Yeah, YouTube has some of the questions which have already been answered. So I just acknowledge the people who have written the questions. One is Arnav Jain, who asks who is Galileo, but Galileo, I mean, it's a very difficult question to, I mean, everyone knows Galileo Galilei. Yeah, so it's very important contribution, of course, in the sunspots and various other things. And some questions are on, one question is, sir, this which I think is very important right now is from Arvind. Sir, can you suggest some experiments to do using radio astronomy with respect to sun? I think that is very relevant. Other questions are, what does a CME consist of? This is from Ishan Deshmukh, but I think this already has been asked and many others have, and you have answered it. And Suraj Tiwari asks, what is a heliosphere? So I think the question about, can you suggest some experiments, I think is very important. Could you just elaborate on that?
Okay, so it depends a lot on the kind of equipment which you have available to you, right? So one experiment, for example, which you might be able to do using, let's say, a dish TV antenna, right? The DTH antennas which we have at home. If you have the ability to direct that antenna to the sun, and if you have the ability to take its output and measure in some ways what is the strength of that signal. So if you could sort of move that antenna such that it is crossing the disk of the sun, you would find that as you're pointing it at the sun, your output has grown higher, and as you move it away, it has grown smaller. If you were to do it on different days, you would find that the amount by which it grows or comes down is different on different days, because the amount of energy being given out by the sun at those wavelengths is different at different days. If you were to work at much lower frequencies, you could probably build dipole antennas, something like Aniket, you remember the name of that NASA kit which they have for low radio frequencies? Yeah.
No, I don't remember often.
Okay, never mind. Yeah, so there was a at comparatively low radio frequencies. Those guys are, I think, something around 50 megahertz or so. You can have comparatively inexpensive equipment using which you can measure the amount of radiation which is being picked up by that. Sorry, that is called radio Jove. That was meant more for the for Jupiter than for the sun, but it would also pick up the sun. Yeah. So those are some experiments which one could think of. And the second question,
There is
Harvinder?
another question from Ishan Deshmukh. Yeah, there is another question from Ishan Deshmukh. So can it be said that magnetic fields of a large body can be sustained by the convection currents of its contents?
Sorry, can you say that once again, please? Yeah.
Yeah. So can it be said that magnetic field of a large body can be sustained by the convection currents of the contents?
Right. So I guess one could say that it's a necessary but not a sufficient condition. So it will depend a lot on the nature of the bodies, on the nature of the convective currents, and so on and so forth. But without some sort of large scale motions of this material, it would not be possible to generate the magnetic fields.
Okay, I have one question here. Uh, so you have spoken about CMEs affecting the Earth. What about do we see any evidence of CMEs affecting other planets? This
Oh,
is
absolutely.
Akash
Okay.
Devangan.
Yeah. That's again a very nice question, a very certainly a very interesting one as well. Yes, so what we are trying to do these days, among the things when I say we, I don't mean me myself, I mean the grander body of astronomers across the world are trying to learn about the impacts of what we now call space weather on these other planets as well. And because these are things which we can study from a distance, and it's sort of easier to make some of the measurements there as compared to what it might be on the Earth, we are using the opportunity to learn what might be the impacts of these CMEs and so on other planets. It's very much an active field of study.
Okay, Harsh has an interesting question. In the movie Mission Mangal, it was shown that the spacecraft, Mongolian spacecraft, was hit by solar storm, and because of which its speed increased. So the question is that you have said these solar storms can destroy communication and electronics. So how can it speed up something?
So I should first confess that I have not seen Mission Mangal. Sorry about that. Yeah. I
Yeah, it was.
so
I think if I remember correctly, even I have seen it long back, but it was shown like it worked as a solar cell kind of thing. That because of the high energy CME which hit
radiation.
that,
Yeah.
so it helped. It worked as a cell, and it could
Okay.
speed up slightly. And it's why
Right.
I roughly remember that.
Okay. So if you are traveling in the same direction as the CME, you will get a push. If you were to travel in the opposite direction, it will hinder you. So it is just like, let's say maybe you are cycling on a very windy day, and if you're cycling along with the wind speed, you get a push. So something similar to that. Yeah.
Actually, the students, high school students, if you look at class 12 CBSE book, there is a mention about solar radiation pressure in class 12th book. So if you use that, then you will be able to work out the simple mathematics behind this phenomena. Uh, then I have a question. Slide.
about there's a question about Aditya L1, which I think is
Yes.
very relevant, how it can be used to study the sun.
Yeah. What is special about Aditya L1?
Okay. So Aditya L1 has a few different things which make it very interesting from solar physics perspective. One of them is that it is going to sit at a place between the Earth and Sun, uh, which is a part of the name of the satellite itself, the L1 point, the so-called Lagrange 1 point, where the gravitational pull by the Sun and the Earth are equal. So it's a place where you can sit between the Sun and the Earth, and you will never see any eclipses. So you can do a continuous monitoring of the Sun from there. One of the things it is trying to do is that it is trying to observe the Sun in a particular layer of the Sun called the chromosphere, which lies just above the photosphere, through which all this magnetic field, which gives rise to all the activity which we see on the Sun, passes. Now that has been, for some reason or another, not as well studied a region of the Sun and the corona. So a lot of the focus is going to be on studying the details of activities which take place there. Now, another thing it is going to try to do is that on the same spacecraft, we will have many different payloads which will simultaneously give us a much more complete picture of what is happening on the Sun. So it would be able to, for example, create an artificial eclipse of the Sun and make movies for coronal mass ejections, just the way I was showing you earlier, except that the current instrumentation, the eclipse which they create, it hides not just the Sun, but in fact a larger region, something like around 2 solar radii around the Sun. While this guy is going to be able to create an eclipse which is, I think, only about 1.07 solar radii. So it's going to obscure only the Sun and not much more beyond that. And that would be observable. And that would also be observable by the other instrumentation which is there, the chromospheric detectors. The ultraviolet light which it is going to be detecting is going to be arising from those regions. So it's simultaneously going to be able to measure many things which have not been possible till now. It also has additional things, bunch of plasma detectors, which are very interesting here.
And I think it will be also ISRO's first mission to one of the Lagrange points, right?
Correct. Yeah. So that in
Okay.
itself is an achievement. So it I mean, from the perspective of getting a spacecraft there and keeping it operational is very interesting, because see, you can't put it directly along the Earth Sun line, because then all the ground stations on the Earth have to be staring at the Sun to look at the satellite, right? So you have to keep it somewhere in the vicinity of that point, but sufficiently far away that when you look at the satellite from the Earth, you don't have Sun in your field of view. So you have to follow a particular orbit and sort of eight-shaped orbit around that place and keep the satellite there. That is an art in itself, and that's something which ISRO is very keen to do.
Okay. What there's one question from Akash. How is chromosphere different from the photosphere?
So chromosphere is just the next layer which sits on top of the photosphere. It got called the chromosphere because that was the region where all the absorption lines which we see in the solar spectrum, they arise. Okay. It is much lower density as compared to the photosphere, and it has a somewhat different temperature profile. It first drops and then rises a little bit. Yeah.
Sarita, you have a question?
Yeah, I just wanted Divya to answer this, because I get students asking me this question, saying about the size of the sun doesn't change, right? It's quite some time. I mean, because there's a lot of energy flowing in from inside, and in principle, you would think that its size should become larger and so on, but it doesn't change day in day out. You see
No,
the
yeah.
same size of the sun. So how does that happen? So there's so much energy flowing in inside, but size is not changing. Why is that?
No, I'm not sure I understand that very well. So you're
In the
thinking
sense that
because the light,
yeah, energy is coming in from inside, but there's something holding it together, right?
right. So it's a balance. So there is energy
Yeah,
trying
yeah.
to flow outside, and there is the gravitational force which is trying to hold it together. And so because the flow of energy is via convection in the outer layers and via radiation in the inner layers, it uh, does not require the sun to change its dimensions. The sun has all sorts of oscillations, right? which we talked about in context of helioseismology, but they are oscillations around a mean, and that mean is pretty stable. Yeah, and the sun is also spherical to a very high degree here.
Yeah, but later stages it is expected to become larger in size, the red giant which is talked
Right.
about.
Yeah.
So that would happen because of.
So
So,
yeah.
Sarita, what probably were right now two parts of the question.
Yeah.
At later stages, probably what will happen is the energy production rate will slightly go
Hydrogen.
up
Yeah,
before.
yeah.
Up,
Yeah,
yeah.
Yeah. Can
yeah.
I come in here? There is another, which is a slightly related question by Suresh Trivedi. Is sun brightness decreasing day by day? So I think we should fold it into this
Yeah.
discussion.
Sure.
So energy production rate will go up in latter stages is one factor, and that will upset this balance slightly. That is why the size will slightly
But
increase.
Increase.
I think it is also because the production will not be in the same region. It will happen outside and so on. Because at the core, the hydrogen fusion will get over. Then it will start in the shell. I think, isn't
Right.
it?
Yeah.
Yeah.
Yeah. I'm sorry. I
But
am a bit rusty on that. Yeah.
yeah, but another interesting thing which the students can calculate, and this doesn't involve any very complicated physics, something which even high school students can do, is even at the short time scale, given the energy which is being emitted by sun every second, in fact there is a slight change in the sun's size. It's so
Mm.
tiny that you will not
Yes. We will not observe it.
you will not observe it, but
Huh.
in principle there is some slight change, so that they can calculate. This is usually a very interesting exercise.
Over the main sequence or the current stage of the sun.
Yeah,
That's what you mean.
over 1 century or 2 centuries, if they calculate, then they will realize even in 100 years the size will not change by more than a centimeter or something like that.
Okay.
Sorry, Harvinder, can you remind us of the question you had? Yeah.
Question is sun's brightness decreasing day by day?
Okay. No, it's not fair to say that its brightness is decreasing. Its brightness does change a little bit. So for example, in the optical, if you have a large sunspot, you see a little bit less. But like we said, these sunspots are also associated with giving rise to other energetic light. So in terms of energy, it gets usually more than compensated in terms of what is given out at in ultraviolet and X-rays and so on. So it has been pretty stable, the energy output of the sun, and over very long time scales, I mean, time scales of centuries, certainly, we expect it to remain very stable.
Okay, I think we are done with most of the questions, isn't it, Aniket and
Yes,
Harvinder?
yes,
Yes. So
and
maybe,
we are also
yeah,
overshot the time.
So let me just give you
we had a
one
lot of questions.
final question from YouTube. What is
Yeah.
Orion spur? So, I mean,
What is Orion spur here?
I think they want the location of the solar system.
Okay. I'm afraid I don't have a great answer to that.
Usually the
If you want to jump in.
spur is a minor arm which connects two spiral arms in a galaxy.
Galaxy.
So,
Right, but I am not going to be able to add much to that.
yeah.
Yeah. So Aniket
In any case, one can, when one
or
talks about
Sarita, yeah.
galaxies,
Yeah.
when one talks
Yeah.
about galaxies, that question can be taken.
Sure. Yeah. My apologies for that. Yeah.
Yeah.
So
So
there
I
is one
think,
question by Akash which has just come. So probably before closing, we'll take that one last question.
Sure.
yes.
Yeah.
How much is solar radiation capable in moving a satellite in interplanetary mission?
Say that again. How much is solar? Yeah.
These interplanetary missions, which when they travel through solar system,
Yeah.
will their path be affected by solar radiation?
Uh, so there are, I think that's something you alluded to earlier also. So now, yes, to some extent it will be, right? There is all this flow of material which is there. It has certain velocity. The velocity is actually few hundred kilometers per second, even though the density is very small. The density is just a few particles per centimeter cube. So it is going to impinge on that satellite and it is going to transfer its momentum. So if you were to say going radially out from the sun, from the solar system, it will help you, it will push you. And in fact, there are concepts of solar sails which are using exactly this to propel spacecrafts to higher speeds. So people are actually thinking of using this idea to build up the speed of satellites on their way out of the solar system. In fact, to take Aniket's sort of perspective, if you can work out how much momentum, if I had, let's say, a satellite with a surface area of, say, a few meters square, and if I have a gas of particle density of something like, say, 10 particles per centimeter cube at 1 AU, and you say it is moving at, say, some 500 kilometers per second, how much momentum it is going to impart to that surface, you can figure out, and that would be your answer about how much speed up you would get here.
So I think we will we have come to end of the session. Harvinder, would you like to step in?
Thanks a lot, Divya, for a very detailed talk on sun, starting from vital statistics, the size and the temperature and the mass, and going on to the coronal mass ejections and how really in our regular day-to-day life also we can be affected by it, and what should be done with the various technological inputs from there. Thanks a lot for your talk, and we will meet in January now on the second Sunday as usual, January 10, with another talk of another session of Ask an Astronomer. And I would like to thank Divya, the team who's live streaming it on YouTube, Atharva and Chris, Sarita, Aniket, and the ASI POEC. Thank you. Thanks a lot.
Yeah. Thank you very much. Thanks, everyone.
Bye.
Thanks to the audience as well. Yeah. Goodbye. Take
Bye-bye.
care. Yeah. Bye.